we're going to be revisiting what we learned last year about direct linear variation. This involves when y varies as x, or y is directly proportional to x, then y equals kx. Where that letter k is, it's a constant. A constant just means a number. And a k is called the constant of variation, or the constant of proportionality. Okay? So basically, if you have y equals kx and the value of x increases, then what happens to y is also, it will also increase. Okay, so whatever happens to x, y does the same thing. So if x decreases, then y decreases as well. And if x is doubled, then y is also doubled. Lastly, if x is halved, then y is halved. Okay, so that's just a simple revision of what we did last year. Now, examples of two quantities that are directly proportional are involving, let's just say, for example, mass and volume. So the heavier an object is, okay, the bigger it is in terms of its volume. So we can say m equals to letter k, which is constant variation, times v. If we have quantity 1, which is speed, and quantity 2, which is distance, well, the faster a car travels, the more distance they're going to cover. So they both increase. Or the slower they travel, okay, then the lower distance that they travel as well. So speed, S, is equal to K D. Okay. Volume of a tank, V, and time. So the volume of a tank, when you're pouring water into it, will increase over time. Okay, so as time goes by, more water will be in the tank, or if time is not as high as before, then the volume would be as high as well. So V would equal to KT. All right, so these are just some examples of quantities that both increase or both decrease, okay, in relation to each other. All right, let's have a look at example 8 from the textbook. The mass m in kilograms of a metal varies directly with its volume. So basically, as something gets bigger, the heavier it is. So we can see that the volume numbers here are getting larger and larger and larger. And as they get larger, the mass is also larger. So the mass of some object depends on the volume. So this is the dependent variable, whereas volume is the independent variable. If we were to graph this relationship between m and v, in your books, you don't really have to draw this, but just letting you know that the volume, which is the independent variable, will go on the horizontal axis. And you can see that it's nice if you can go up by 10s or 20s, okay, getting up to number 140. And if you go up to 140, then you only need 7 spaces, okay? Then if you look at the mass goes up to the number 42, so you can go up by 5s as they've gone here on the vertical axis, and then just plot each coordinate, so 0, 0, 48, 14.4, 60, 18, and so forth. Now, joining all these dots together make this straight line, okay, which is a linear relationship that relates the mass of some metal with its volume. So if we're asked to find the equation of m in terms of v, we need to actually establish that m, which is the dependent variable, is equal to the constant variation times by the volume. So m equals kv. And once we do that, we have to substitute in something that relates m and v. So we just got to get a pair of values. It doesn't matter if we substitute in any of these except for 0, 0. Because if we substitute in 0, 0, then there's just 0 equals 0, which means you can't even solve for k. So we're going to substitute in something nice, okay, something that doesn't have decimals maybe. Substitute in 60 and 18. So if I substitute in 60 and 18, meaning that volume is 60 and the mass is 18, 18 would equal to k times 60, which means that what you've got to do next is you divide 60 to both sides to eliminate that 60. And so K would equal to 18 over 60. And that simplifies simply to 3 over 10. And now once we've done this, we can now substitute this K value back into the equation. So that M is now equal to 3 over 10 times V, or you can say 3V over 10. Right? Or this could also be M equals to 0.3V. If we type 3 over 10 on a calculator, we do get the 0.3. And once we've actually generated this equation, we can actually find out either M or V given one or the other. So in the first question afterwards, it says find the mass of 212 cubic centimeters of the metal. So how heavy is it if we've got this kind of volume of metal? Well, we're going to substitute this into the equation. So we'll just substitute it into this one here. So we have to find the mass when V, in this case, which is this one, oops, so that is equal to 212. Okay, I repeated that 3 by accident. There we go. So M would equal to 63.6 kilograms. Okay, so the mass of this metal is 63.6 kilograms if its volume is 212. Let's move on. Example 9. The stretch S in centimeters of a spring varies as the mass M in kilograms of the load pulling it. A load of 24 kilograms causes the spring to stretch 15 centimeters. So let me just draw that out for you. So let's just say this spring is attached to the ceiling or something like that, or some kind of object on top. And then there's a spring, all right, which is attached to some load. So this is the load. And what happens is this load in this example is 24 kilograms, and it's forcing this spring to stretch 15 centimeters. And you can imagine that if this load is actually like more heavier, let's say it's a bigger load, then it's going to stretch to this much. Okay? So the heavier the load, the more the spring will stretch. So let's find a variation equation relating S to M. Now, we have to write S, first of all, which is the stretch, and that depends on the mass. So we write Km. Then we got to substitute in a pair of values. So we can see that a load of 24 kilograms, which is the mass, is causing the spring to stretch 15 centimeters, which is S. So I can substitute the mass in here and S value in there. So 15 is equal to K times 24, which now allows us to find K by doing the opposite of 20 times multiplying by 24. And we'll do that to the other side like that. So we divide both sides by 24, and this will disappear. So therefore, K would equal to 15 over 24, which does simplify to give you 5 and 8. Okay? Or you could even write down 0.625 only if it's a terminating decimal. Okay? So, therefore the equation, okay, if I was to just use the decimal, it will be 0.625 m like that. Okay? Now for question B, what is the stretch caused by the load of 30 kilograms? So this refers to M. Okay? And we're finding S. So M is now going to be 13, and we're just going to substitute that in there. So S would equal to 0.625 times by 13. Okay? And what that will give me is 8.125. Don't forget the units. The units that it said for S was centimeters. So we're going to write centimeters. Okay? Question C. What is the mass of the load that will cause a stretch of 25 centimeters? Okay, so if this is stretched 25 centimeters, that would mean that the load will be more heavier than this. So let's have a look at that formula again. So S equals to 0.625 m. But now we're finding out the mass, okay, when the stretch here is 25 centimeters. So we're going to replace S here by 25. That's equal to 0.625 m. And in between the 0.625 and m is a multiplication sign, divisible. So we're going to do the opposite of that. So we divide both sides by 0.625, like so. And then this will cancel out. So m would equal to 25 divided by 0.625, which is the number 40. Okay, so that means the object that is pulling it down is 40 kilograms. Okay. Now, generally speaking, all these questions that you will get in the exercise will be of this nature. So first question is find the equation, and the second and third question will be find one letter, and the other question will be find the other letter after that. But at the very end, sometimes we will ask you something about this equation. When it's a limitation, for this example, or maybe what is bad about this equation that might not work, okay? So just remember that this is a spring, okay? And that spring might be, you know, not unlimited in centimeters. So what happens if this is fixed, okay? If this is fixed and you have something here that is like maybe 50 kilograms, let me just draw that out. Okay, so it's like that. Let's just say it's 50 kilograms, and it's pulling it. Okay, and it's almost straight, right? Okay. Let's just say after like 60 kilograms, it's going to pull the string really straight. Okay. Now, what actually happens if this is now 100 kilograms? What if this is now 100 kilograms? It's going to be the same thing, okay? So that means for some particular mass values, that when they're large, the spring distance is going to be the same. So at higher masses, the formula might not be applicable, okay? So we can say that. So we can say for a spring that is fixed in distance, it will stop stretching. After a certain amount of load, is pulling it. Okay. Another solution could be that once this heavy load pulls this spring down, it will be permanently stretched, and then it won't actually go back. So if I just remove this load, that spring is going to stay there. It's not going to return to its original form, okay? Because it's pulled so much that the metal has been stretched too much. So it won't be going back to its normal form. So we can say for a very heavy load, the spring will become permanently stretched and will not return to its original length.